Hello everyone, welcome to this KANPUR-NPTEL online course on spacecraft environment and its effect on orbital spacecrafts. So, in the last session we discussed how the solar wind is coupled to the Earth's magnetosphere, and in the event of solar activities like solar flare, coronal mass ejection and solar energetic particles, how the phenomena of the geomagnetic storm as well as geomagnetic substorm happens. Along with this, we discussed what are the different matrices to know what is the magnitude of the geomagnetic storm, that is the geomagnetic indices like K index, Kp index, then DST and this image. So, these are the different indices we discussed. In today's topic, we are going to discuss Earth's radiation belt. Already I mentioned about the Earth's radiation belt in our last session, when I was discussing about the geomagnetic storm and geomagnetic substorm and its indices. So, here today along with the Earth's radiation belt, we will discuss the ring current, which is also very important to quantify the geomagnetic storm. We will also discuss the South Atlantic anomaly. So, what is Earth's radiation belt? So, this is also known as Van Allen radiation belts, and this is named after the scientist or the engineer James Van Allen, who led the team for designing the instruments and studying the radiation data from the Explorer 1 in 1958. So, the Earth's radiation belt, this is the regions of high concentration of energetic electrons and protons trapped in the Earth's magnetosphere. So, as can be seen, already we explained how the solar wind is coupled to our Earth's magnetosphere. So, what is happening whenever there is solar wind, our Earth's magnetosphere it offers an impenetrable barrier that prevents the fastest and most energetic electrons from reaching us. So, basically this is because of this trapped charged particles known as the radiation belt. So, you can see there are two belts. So, this is the inner radiation belt and this is the outer radiation belt. So, these two belts are they are the distinct and are of toroidal shape surrounding the Earth. So, this is basically in 2D. So, if you consider it 3D and you see from the North Pole, you will find it is something like forming a toroidal or the donut type shape of the layers which surrounds the Earth. So, what are the sources of this trapped particles? So, the primary source or the stream of particles, this emanates from the sun surface, that is called the solar wind, that already we explained in our yesterday's session. And also the source is also the galactic cosmic rays. So, galactic cosmic rays are the energetic particles, that is particles of heavier mass, that is released by this a phenomena called the supernova. So, this is these stars which are outside our galaxy, and when it comes from the extra that is galactic stars. So, these are very high energy particles, this also enters to our atmosphere. So, this also contributes to the trapped particles. So, basically the trapped particles are mainly energetic electrons and protons. Other nuclei such as alpha particles, they are also there, but they are less dominant. By trapping the solar wind or the cosmic rays, the magnetic field deflects those energetic particles and protects the atmosphere from the destruction. So, the outer belt, it is made up of billions of high energy particles that originate from the sun and becomes trapped in the Earth's magnetosphere, whereas the inner belt, it results from the interaction of the cosmic rays with the Earth's magnetosphere. The outer zone is very dynamic and the electron lifetime ranges from minutes to years, whereas the inner zone is more stable and the lifespan it can last up to 100 days. Now, let us know a little bit about the inner and outer belt, how long it stretches. So, the inner belt, inner radiation belt, that is IRB, it is located between 1.1 to 2 earth radii. So, 1 earth radii is something like 6,371 kilometers. So, from 1.1 to 2 earth radii, and mainly it consists of the electrons with high energies up to 10 mega electron volts, and with protons energies up to 700 mega electron volts. The outer radiation belt, or acronym you can use the ORB, it starts from about 4th earth radii and extends up to 9 to 10 earth radii in the anti-sun direction. The outer belt consists mostly of electrons whose energy is below 10 mega electron volts. Now, let us try to understand how these radiation belts are formed. So, again we will see this, this is the image or the cartoon where the solar wind is getting impinged on the magnetosphere. So, as you know, most of this solar wind will be directed or will be deflected around or away from the planet, and it cannot penetrate the region, that is the magnetosphere. However, some particles, as you can see, some particles will gain some entrance through the polar region, because all the magnetic field lines which deflects the charged particles, some of the charged particles can enter to the magnetic fields in the polar region, and this becomes trapped in the Earth's magnetic field. So, these are the, you can see this is the trapped region. So, this region and this region, how it is getting trapped? It is taken because these charged particles, they are entering to the magnetic field in the polar region. So, these trapped particles are contained in one of the two donut shaped magnetic rings around the Earth. Now, let us try to understand what is the particles motion and what is the dynamics of these trapped particles in the radiation belt. So, here a blend of 3 periodic motions this take place simultaneously. The first one is the first rotation or the gyration around the magnetic field lines, typically thousands of times each seconds. Then the next phenomena, it is a slower back to forth bounce along the field lines, typically lasting for 1/10 of a second. Third dynamics, what happens is it is a slow drift around the magnetic axis of the Earth from the current field line to its neighbor, staying roughly at the same distance from the axis. Typical time to circle the Earth is a few minutes. So, we will now see each of those dynamics one by one. So, first is the rotation or the gyration around the magnetic field lines. So, as you know, that is, if the electrons and ions which are commonly encountered in the magnetosphere tend to circle around the magnetic field lines. So, whenever charged particles, they are moving at some certain velocity in a magnetic field, then the phenomena of the gyration happens. You can see there is a magnetic field B, and there is a charged particle which is having the velocity components. One is the parallel to the magnetic field, and the other one which is perpendicular to the direction of the magnetic field. Now, whenever the particle is moving, so there will be a gyration. So, it will circle magnetic field, and whatever you know that a solenoid is formed, and that solenoid, the axis of the solenoid will be the magnetic field line. So, like the motion of planets around the sun, this motion too can sustain itself with no energy input and can therefore in principle persist for long time. So, this gyration, it does not need any extra energy. Once it is trapped, it will gyrate. So, opposite charges, that they circle in opposite directions. Okay, we will see it. So, you can see the positive ion, it is the sense is counterclockwise, whereas the electron, it is having clockwise. So, their the sense of rotation is different. So, positive ion it is anticlockwise, whereas for electron it is clockwise. Now, if we see the physics why this is the trajectory of the charged particles, why it becomes like that. So, it is because of the Lorentz force. So, whenever a particle is moving in a electromagnetic field, so it experiences a force. So, the electrical component of the force is the charge multiplied by the electric field intensity, this one, and the magnetic field it is the force is it is the vector product of the velocity as well as the magnetic field, okay, and that is multiplied by the q. So, this is called the Lorentz force. Now, let us assume a condition. Okay, before that let me explain. So, dp by dt is basically your force. So, this is as this I can write is basically it comes from the momentum is m into v, and since the v is here it is the relativistic, means the velocity is a fraction of the velocity of light. So, we need to have this factor to take into account the relativistic momentum. So, what was the point here? Suppose this E field is there, E is not there. So, what happens whenever a particle is moving with a velocity v, and assume that the velocity v is perpendicular to the magnetic field direction. So, in this case the magnetic field is directed towards the paper. So, in that case there will be a force F towards the center of or inwards. So, inwards like this is the point. So, what is happening because of this force is now perpendicular to the velocity. So, it will not have a tangential, the tangential velocity will be there, and as a result of this force it is something like a centripetal force. So, centripetal force is nothing but here the magnetic force. So, because of that centripetal force we will have a circular motion. Now, what will be the radius of this circle? It will be decided by what is the magnitude of the magnetic field, what is the charge, okay, and what is the number of times charge will it will circle, that will also we can get it from the angular velocity. So, in the next slide I will show you those things. Now, suppose that the velocity is not perpendicular to the magnetic field direction, but there is a parallel component, and in that case already I told you that will gyrate. So, this case shows here the magnetic field is not uniform. Whenever the magnetic field is not uniform, the radius of that gyration will also change as well its frequency. So, you can see its radius is decreasing, but the frequency is increasing. So, in that case the frequency that is it is increasing, and the radius that is we will call it the radius of gyration that is decreasing. So, let us now see what is the gyration radius and the cycloid. So, this will be the gyration radius, this will become the gyration radius, we will call it R L. So, we can calculate the gyration radius. So, we can form a simple differential equation, and we can solve this to get this expression, that is also called the Larmor radius or the radius of gyration. So, where m is the mass of the particle in kg, then q is the charge in coulomb, and b is the magnitude flux density, and we will show that we will use in this expression we will use it the unit as the Tesla. And b perpendicular is the velocity component perpendicular to the magnetic field direction. And what is the frequency? That is, a particle will the number of revolutions it will do per unit time. So, that is called the gyro or the cyclotron frequency. This expression also can be derived. So, this is this expression. So, a gyration period is the time for the particle to complete one revolution around the field line, and this is the expression. Now, let us solve. And another point I like to tell you, this center of the circle, that is called the guiding center. Okay. So, let us try to this as an example. So, determine the gyro frequency, the period and the Larmor radius of the solar wind electron moving in the geomagnetic field. So, this is the magnetic field intensity at a speed of 400 kilometer per second, and we will assume that is the direction is the perpendicular. Whenever nothing is given, we will assume that is the direction is the perpendicular. So, first what are the things given? So, m, that is the mass is of electrons. So, here it is electron is mass of electron, that is equal to m is equal to 9.1 into 10 to the power minus 31 kg, and this magnetic field, given magnetic field is 2000 nano Tesla, means 2000 into 10 to the power minus 9 Tesla, and the charge of an electron q is 1.6 into 10 to the power minus 19 Coulomb, and V t, V perpendicular is 400 kilometers per second. So, this I can write 400 into 10 to the power 3 meter per second. So, we can calculate the frequency, that is the gyration frequency f g is equal to q b by twice pi m. So, if you put or substitute these values, you will get a figure 56.4 kilohertz, and the Larmor radius R L, the Larmor radius is equal to 1.1 meter. Okay. So, next is how this bouncing back and forth between the mirror points happens. Let us try to explain this. So, as such the particles that circle around their guiding field line or the guiding center, and but the rotation generally slides up and down that line, creating a typical spiral pattern. However, the spiraling particles get repelled from the regions of stronger magnetic field, where the field lines converge. So, here what happens, whenever charge is entrapped, it is moving in the magnetic field is not uniform. So, the magnetic field that is the intensity of magnetic field is more in the polar region, and when it is going away from the polar region, the intensity decreases, and it can be shown that the velocity, that is the velocity along the magnetic, that is the parallel component of the velocity reduces, and the perpendicular component of the velocity increases when a charge moves in a non-uniform magnetic field. So, this gives an effect is called the magnetic mirroring. We will try to see what is that. So, what I mean to say, that the particles is repelled as it moves in the region of stronger field, it advances along its guiding field line and it slows down. So, you can see whenever it is moving in this with the magnetic field with the guiding center, then what is happening, whenever it is going to towards the intensity is increasing. So, what is its speed is, the speed is getting reduced and it is getting slowed down, and at some point it becomes 0 and then it gets bounced back. So, you can see here, we can see here it is going in this direction and then it is getting bounced back. So, it is coming like that and getting bounced back, and the sliding velocity finally drops to 0 and then reverses, causing the particle to bounce back, and so these points are called the mirror points. So, where the intensity of magnetic field is more, so these points are called the mirror points, and because of this mirroring, these effects, only these charged particles are trapped. Otherwise, these charged particles would have to flow there, instead of flowing to their guiding lines into, they would have entered to the atmosphere, where they would have absorbed and they lost. What usually happens, that every time a trapped particle approaches the earth, it is reflected back, so that it is confined to more distant section of this. So, that is why it is confined to this section. So, what is the third, the dynamics we said of the trapped particles, that is the drift around the earth. So, in addition to the rapid rotation or the gyration around the field lines and back and forth bounce motion, the tapped particles also undergo slow drift. So, what is that? Let us try to see. So, what is happening? There will be, so this is the tapped, there is the tapped motion and it is bouncing back and forth. Along with that thing, what is happening? There is a drift along the drift in the longitudinal direction. So, because of this what happened, by which the jump from one field line into the another one nearby similar to the original, but slightly rotated around the Earth's magnetic axis. So, if you view it from this north side, from here if you view it, you will find a picture like this. So, if you can take just a cross section, you will see the field lines will become like this. So, now if we summarize these three motions, so this is the gyro motion. Whenever the magnetic field lines is there, so it is it is tapped or it is gyrating with making the guiding center at the magnetic field lines. Whereas, in this case, when the magnetic field lines they are having the intensity is changing, it is converging. So, we have a, that is the bounce back from this or the reflection from this point, it is getting reflected, again it is getting reflected from this point. So, you are getting a, that is the mirroring effect, and the third is the drift of motion, that is this thing is getting drifted along the longitude of the drift motion with the magnetic axis of the earth magnetic axis at the center. Now, let us explain what is a ring current. So, already I mentioned yesterday, that is from the ring current variation, I got an indication of what is the strength of the geomagnetic storm. So, whenever there is a geomagnetic storm, as I mentioned, there is an increase in the ring current, and the magnetic field produced by the ring current is opposite to that of our geomagnetic field. And as a result of that, in the case of a very strong geomagnetic storm, this overall magnetic field can go to the negative side. So, this gives an indication of what is the magnitude of the geomagnetic storm. So, under the influence of the magnetic forces, the ions and electrons drift around the earth in opposite directions. So, this has been shown. So, here this drifting for the electron and the protons, they will have in the opposite directions. So, because of the positive ions and negative electrons drift in the opposite directions, this motion will create an electric current, and that will circulate clockwise around the earth when viewed from the north. Whenever you view it from this north, you will find that is a clockwise current. So, this is the clockwise current. So, because the current direction we assume, that is the positive, that is the direction in which the positive charge moves, that is the direction of the current. So, in that case we get a that is the, so if I draw it like this, so this will be the direction of the current. So, this current is known as the ring current. So, this shows this picture also shows very clearly what is the direction of the ring current. So, this is the direction of the ring current, clockwise direction. So, already I said at an intensification of the ring current, it happens during the magnetospheric disturbances like geomagnetic storms, and this current will generate a horizontal component of the magnetic field opposite to that of the geomagnetic field. For in that case you get a that is the overall magnetic field during geomagnetic storms, it can give a negative perturbations, and which is called the DST and the CMH, from which this DST and the CMH indices can be derived. Okay. Now, there is one phenomena or one term, it is used in the radiation belt, that is called the South Atlantic anomaly. So, South Atlantic anomaly means there is a portion upper atmosphere where this magnetic field is weak. So, this is the region where the magnetic field is weak. So, there the inner radiation belt, its altitude, it reduces by 200 to 250 kilometers. So, this region is called the South Atlantic anomaly region. So, this is an area where the Earth's inner belt, radiation belt, comes closest to the Earth's surface, dipping down to an altitude of around 200 kilometers. The South Atlantic anomaly is the near Earth regions where the Earth's magnetic field is the weakest, as I said. So, the here is the weakest, and this is this leads to the an increased flux of the energetic particles in this region, and it exposes the orbiting satellites, including the international space stations, to higher than the usual levels of the ionizing radiation. And it is caused by the concentricity of the Earth with its magnetic dipole. That is, the magnetic axis is, it does not coincide with the Earth's axis of rotation. So, it is away by 11 degrees. So, with this let me conclude the session. So, in this session we have explained what is the radiation belt, two belts mainly, the inner belt and outer belt, and we have seen what is the dynamics of the trapped particles inside the two belts, Then we explained what is the ring current, what is its significance in the space weather, and what is the South Atlantic anomaly. So, in the next class we will start explaining, that is the different type orbits and what is its characteristics, what is the space weather effects. So, thank you very much.